welcome back. And we'll try and finish this off now with the last little bit of material that's in the first slide deck that I posted. Tying into the stuff on scientific notation that we talked about in the last one, we've got an alternative approach to writing out in scientific notation numbers by using what's called the metric prefixes. Now, unfortunately, my closed captioning is covering over the top part of this, but all this says is metric prefixes. And we've got in the table here a list of common scientific notation multipliers, prefixes, and the abbreviation that go with it. So what we do when you have a number that's written in scientific notation, and instead of writing it out in scientific notation, you'd like to write it in this form, you simply replace the power of 10 multiplier with its corresponding prefix and attach that then to the base unit. Most commonly, because again, the way we group our numbers in our number system is to go by essentially powers of 3. Most of the common prefixes are, again, multiples of 3. When you get down to around powers 1 and 2, you will encounter those individually, but as you go up into the bigger range, either getting bigger or getting really small, they typically just go with the multiples of 3. So, for example, if we have a measurement of 1.5 times 10 to the 3 meters, rather than writing out the times 10 to the 3 part, we can come over to the table and see that times 10 to the 3 is kilo. So we use the kilo prefix in front of the meters, and it becomes 1.5 kilometers. That is a quicker way of writing our number, and as well, we can then easily convert back and forth between the prefix form and the scientific notation form. You will commonly encounter things like the kilo, the mega, giga prefixes. Likewise, we commonly see centi in centimeters, milli, micro, nano. These aren't unusual at all, especially when you get into electrotech and components in electric circuits. So these are ones that are useful to commit to memory, especially, again, tera and peta aren't all that common. Likewise, well, femto isn't all that common, but even pico will show up occasionally in electrotech. Nano, certainly. Next, the concept of significant figures. Now, I will freely confess that significant digits, significant figures, I use those terms interchangeably, significant figures will not be something you're going to enjoy in all likelihood. I know in my university career, significant digits and the calculations involved in that and what we call error analysis made life pretty miserable, in the lab especially. The good news is, in physics, we're going to make life a bit simpler for ourselves and for you. I can't make the same promise for chemistry. So this is going to be one of the reasons why you like physics better than chemistry, aside from your instructor. Hopefully you have Tony, because I make fun of Tony a lot. So significant figures, it comes down to the idea that when you do a measurement, certain digits are digits that you actually measured. Whereas others may be there, especially zeros, as placeholders, as filler. So what we need to do is make the distinction between numbers that were truly measured and numbers that simply are there to take up space when we write the number out and act as placeholders in order for the meaningful digits to be in the right spot in the number. So the other aspect to it is the idea that, well, anytime we make a measurement, there's going to be a degree of uncertainty involved, meaning that depending on the tool and the technique and the skill of the person doing it, we can only record down to a certain level of precision. So if you're using a common ruler to measure the width of a coin, say, when you make that measurement, you're judging, well, is one edge lined, the zero on the ruler, is that lined up with one edge of the coin? Then you're looking at the other edge of the coin and judging where that lands on the scale. And you have to make some estimate then of, well, what number does that actually represent? Some of that information then is effectively encoded into the way you write your answer. Now, the rules for significant figures. What that means is that when we write our answer, when we write our measurement down, we need to specify, or we are specifying, when we write down a number, we are making the claim that it is significant. So anything that isn't a zero, it's implied, it's understood that that number had to have been measured. Otherwise, you wouldn't have written it down. So if I wrote the number 321, it implies that I measured all three of those digits, and therefore they are significant. It's zeros that make things complicated. And in fact, I'm going to skip these 2 points here that come up next and jump down to the ones that are later, because the ones that are later might make a little more sense at first. So zeros that lead a decimal. So for example, 0.0234. These ones at the front, we didn't necessarily measure them. They're just simply there to be able to place the decimal where we need it to be. And in fact, we could eliminate them if we converted our unit, in this case, to a smaller unit. So for example, if this was a meter, so if this was a measurement of 0.0234 meters, and I converted this to centimeters, it would become 2.34, and the zeros disappear. They're not meaningful, they're just placeholders. On the other hand, if you have a zero between non-zero digits, then that has to have been measured. It has to have been counted along the way. So for example, if I'm counting along my scale and I go from 198, 199, 200, 201, 202, 203. I've counted that zero in the middle is needed to actually represent the correct value. So it's a measured zero. Zeros aren't always placeholders. They can be measured. It's just they are quite commonly placeholders. Being in between two non-zero digits tells me it's not a placeholder, it's a measured value. Going back to the earlier rules for a second, zeros that trail a decimal number are significant. And that's because what we basically do to kind of give ourselves the distinction is to say that if I place a decimal and then start writing zeros after it, wow, closed captioning didn't really get that one very well, did it? If I place a decimal If I place a decimal, then zeros after that, I'm saying I measured these zeros. These are meaningful. Putting the decimal place in is the way in which I express that. Whereas if you have zeros that simply trail a whole number and there is no decimal point there, then those zeros after the whole number are not treated as significant. We don't know if they were measured or not. So that second point there, that second bullet, is what's known as the ambiguous case. We have no way of knowing if those zeros were measured or not. So we have to treat it as one significant digit. If you want to make sure that it's clear, rather than write it as 200, we would write it in scientific notation and say 2.00 times 10 to the 2. That would confirm that in fact those zeros were measured. If not, we would just simply write it as 2 times 10 to the 2. That eliminates the placeholders. As I said, we're not going to spend a huge amount of time worrying about significant digits, and that's not because we're lazy in physics. It's not because we don't care. The trick is that in physics, that the trick, not Ricky, trick. The trick is that there are so many factors at play in the physical universe that if we go out into the lab and do an experiment, we cannot possibly account for all the little things that could affect our results and affect our measurements. We can do a really good job and get pretty good results. And if you have multi-million or multi-billion dollar equipment in a very high-end research lab, then yes, we can get very, very precise results. But in everyday life and everyday physics labs, we don't get that level of precision. So that means, for the most part, the work we'll do, 3 significant digits will be plenty to express what we can actually claim. And sometimes we won't even be able to get that good a result. Whereas in the chemistry lab is all about precision and controlling the environment to ensure that you have control over all the factors and can get values to that level of precision. So in that case, yeah, you do need to be more careful and more responsible with your significant digits. For the most part, in our case, we just tell you to do everything to 3 significant digits, and as long as you know your rules for understanding what is and isn't significant, we don't have to worry too much more than that. That ties into the concept of, again, what I mentioned there about measurement error. Again, this is something that we're not going to incorporate too much into our own calculations, but you will encounter it maybe a bit more in electrotech, in the sense that aside from the precision element that we account for with our significant digits, there's also a recognition that any measurement, any technique, will have a degree of uncertainty, a degree of error built into it, and we need to kind of report that and understand that. So that error, that amount you could be off by when you do a measurement, a common way to quote that is in terms of what we refer to as an absolute error. So this first form that we have here, 12.22 plus or minus 0.01, that's saying that I'm measuring, in this case in centimeters, something that's 12.22 centimeters long, but my measurement could be off by as much as 0.01 centimeters high or low. So I'm really saying it could be 12.21 or 12.23, or any value in between. The other way of doing it is what's called a relative error or percent error. So our next example here, 5.49, what we're really saying is take 1.3% of 5.49, and that's how much I can be off by either way. Each technique or each way of writing this has its own reasons, mostly in terms of how you can take that error calculated forward. So if I measure two values and then I want to do a calculation based on those two values, I need to, strictly speaking, incorporate those errors into my calculation so I can determine how much error there would be in my final answer. Now, this is where the fun really starts when you're doing lab work in physics. Again, the good news for you is we're not going to flog you guys to death with this. We don't need to put that kind of focus on it in the lab. We do point out this concept, though, that none of these measures are absolute, and there's going to be some uncertainty, some error built into all these results. As you move through your programs, depending on which program you're in and which other courses you'll do, that concept will get brought forward again, and you'll need to be able to come up with error estimates or error calculations to account for how much results could be off by. But we don't spend enough time on it in this course to really justify the time and effort we put in now to cover the rules if we're not then going to incorporate it all the way through. So we introduce the concept here, but we don't really go too much further than that. Maybe a little bit every once in a while in the lab, but that's about it. And the last point before I clue up with this slide deck is a quick distinction between what we refer to as scalar versus vector quantities. So sometimes for a property, all we need to do to completely measure a property is to give you a number and its associated unit. And that fully describes what we're talking about with that property. However, for anything that requires a direction element to fully describe it, there we're talking about something different. So in the first case, if we only need a unit and a number, we call that a scalar quantity. And a good example of that is temperature. We can say positive 10 degrees Celsius. We can say negative 12 degrees Celsius. We've got a number. We've got a unit. That's all we need to fully describe what we're trying to talk about. But if we need to include direction information to describe what's going on, in that case, we could refer to that as a vector quantity. And a good example of a vector quantity is the idea of a position. And so if I wanted to tell you, relative to where you are standing right now, there's a pot of gold out there somewhere, and it's exactly 48 meters away from you. Now, that's not much help, because now you've got to say, well, 48 meters in what direction? Because otherwise, you could be walking around all day trying to figure out, okay, where is this thing that's 48 meters away from where I'm standing right now? Well, that makes a big circle. So if we include the direction information, then that becomes a vector quantity. So if I said it's 48 meters due north, now you know exactly where to go. Or in the example on the slide, 5.6 meters. So that's the distinction between a vector and a scalar, and we'll see when we get into not so much the next unit in what we call one-dimensional kinematics. We can kind of ignore the direction component of it to a certain extent, because we're only going to be going in one dimension. one direction overall. Whereas later on, when we get into two-dimensional, now we're going to have to account for directions and split it up into the different directions in order to be able to do the calculations. And it will mean a shift in the way we do the math. We're going to have to shift from simple scalar quantities or simple arithmetic to do the calculations, and we're going to have to get into vector calculations, which is going to require some trig. So hopefully, by the time we get to that, you'll have reviewed your trig in Math 1700, and we'll be able to polish it up a little bit more, and we'll be good to go with dealing with vector quantities. That finishes off this slide deck and the introduction to physics component, and next time we'll be starting on Unit 2, which, as I mentioned, is one-dimensional kinematics, which is essentially the study of motion. And we'll see you then.